Hello YouTube. If you remember, we left off at Ansys Maxwell and we finished modeling and excitation, boundary and setup for the simulations in Maxwell side, and we have done an in detail electromagnetic simulations in Maxwell. Now I want to show you here that in a separate video and tutorial to how to basically import whatever you had and also export the extracted equivalent circuit, or let's call it ECE, of your circuit into the Simplorer. So the environment that you are seeing at this moment is Ansys Simplorer, and what I have here is basically an equivalent model of on the left side we have the electrical equivalent model of the test bench, and on the right side we have the mechanical equivalent model of our test bench. I will go through the details that how I made these things, but before that you may ask that why I need to do more simulation in Simplorer. One of the main reason is you can in the Simplorer do easily add like excitations like the voltage that you will do in the real life, and you cannot do that in the Maxwell. I mean, you can do in Maxwell in a way, but you cannot have a time a function of time excitations in a nice way, and you cannot have a resistor next to that in parallel in series that basically represents the parasitic resistance of your voltage source. And also you can have this amp meter here that you cannot do it actually in the Maxwell easily. You can actually use the calculator to calculate the currents that goes through the wires there, but it's very tough to do that, and no one is actually doing that way. So most of the people are basically doing an in details electromagnetic simulations inside the model that they have, and then they bring those results out, and they do a hierarchical how do you call it, hierarchical simulations on the top of that, and those in this simulation they just take care of the current and voltages and like and the mechanical side, and they just deal with the parameters that they got extracted from the electromagnetic simulations done by Maxwell. So to shorten up this tutorial, I'm gonna first tell you how to bring this stuff and like basically excite your Maxwell circuit. Before I do that, I want to show you how to bring the circuit in, because that's the most important thing that we are watching at this time. So to do that, you go to the Simplorer circuit, and then you go to the sub-circuits that you are going to add into your Simplorer test bench. Under this menu, you go and search for Maxwell Component. And inside the Maxwell component you have different sides. You have dynamic inductance that basically works with the matrix only. So this is the matrix for when you're having the magnetostatic simulation, and this is when you have the DC electrostatic simulations. You have a capacitance matrix and you have inductance matrix in the magnetic side, and over here you have the equivalent circuit, which can have any other parameters that you want or combination of parameters. So that's what we are doing at this time. So I'm going to click on add equivalent circuit. So when you do that, it will ask you what is the equivalent circuit of Maxwell that you are going to bring it in. Where is the file for that? So you basically go on the browse, and when you do that, right now I'm in the Maxwell side of my folder, and I have the Maxwell file for the actuator. So I go and say open this one, and then I want to have you know that my design is 3D, so I will say I have a 3D design. As soon as I do that, it will recognize the design in the Maxwell, and it will say okay, now you can extract the circuit from that. As you can see, it just switched into the Maxwell and opened up a script inside the Maxwell that is asking for exporting the basically equivalent circuits. So the model that I'm using, make sure that this is linear motion, and then for the parametric sweep we have the parametric sweep setup 1, the solution setup 1, The matrix setup is a matrix 1, and the force setup is the force 1. The component that we are interested in is not X, it's basically Z, if you remember from the previous tutorial. And the current variation representation, we go with the ampere per turns, because that's how we defined it. So we say next to that, and since we don't like to have the Fx or Fy as our output, so we just say we just click on the IO part of that and say unused, because we are not using that. And also for the magnitude of force, we are not going to have that as an output, so you don't need to bring it out there. So basically you have inductance here, and you have the current. So now you can use this Bezier interpolation for having more accurate interpolation results, since you have a number of solution nodes, and for any other data that is required you need interpolation. So I think by default it does the linear interpolation, but you can actually ask for the Bezier interpolation if you think that your system is very non-linear. That's up to you. And also you can export the tables out. This is the option that you have. It's optional, you don't need to do it right now, but if you need it, you can actually click here and do the rest. So I'm going to say next to that, and then it goes with the scaling factor. Of course, the scaling factor here is 1. We already designed everything in inch and exactly the size that we wanted. But one thing that we haven't designed was, if you remember, for the coil, we had a stranded coil, and we applied the current in ampere per turns. So now it's a time to say how many turns our coil is going to have, because that will determine our inductance value, and therefore it will change the stuff. So you can right now here say, you know, the number of turns here is like 20, so I have 20 turns. Okay, so that will give us some inductance value that we can work with that later on. Force 1 and the gap is also the other two. So these are the basically electrical parts, and these are the mechanical part. And note that here is we have something called conservative variables. The conservative variables are the one that the variables that are input and output. The simulator, the Simplorer will do another simulation on that to make sure everything is fine. And in this case, if you look at that, you have a current as an input, and then the output of the current is the EMF or flux. So it basically do a recalculation of these fellow numbers depending on what you get as in your test bench in the Simplorer. So that's why these inputs are called conservative ones. Okay, so that is done. I just put the number of the turns, and then you can say finish to that. And now we have nothing to do with the Maxwell side. We go back to the Simplorer. But I have to tell you one other thing, that if you get an error and it says that in the very first stage of that, and it says that you have to solve the equations before the variables before you can actually define or extract them, it's because it's not your Maxwell model. For some reason you either change the folder or change the Maxwell file, or delete the folder that you had all the results saved in it. And if you look at here, we have the solved version of the Maxwell on the top. That means that it's already solved here, and all the models and all the solution is here. So if you right click on the results, you can actually see the solutions, and the solution data is right there. So if you right click in your case and you don't see the solution data, you cannot extract it unless if you run the Maxwell again. It will take some time to solve the data, and then you can actually redo what I said and it will work for you. Okay, so let's go back to the Simplorer. And in the Simplorer side, we have nothing else to do except we want to also double check we also want to go to the options here, and actually we don't need to do anything at this time. I just say okay to that, and I got my basically 4-pin equivalent circuit of my Maxwell side. So I'm just clicking on that, and right there we have all the connections because I already done that there. So you have the current side on the left, and you have the force and the mechanical side on the right. So now it's how you can bring this stuff in. So if you're already familiar with the Maxwell, you don't need to go through that, but the Simplorer. But if you're not familiar, basically you have a bunch of components here in this menu here, and as you can see, we have all kind of different like materials and like components here that we can work with. For some reason my mouse has stopped working. Okay, I think the battery is not working well. So so one way to bring the stuff here is here. So for example, if you need let me change the battery of the mouse and then come back to you, I guess. 1 second. Okay, I changed the battery, so now the mouse is working well. And as I said, you can find a lot of components here. And if I expand this one, you can see that, for example, for the circuit, you have electrical, you have ideal switches here. You can have a preview if you hover on the top of that. You have passive elements like capacitors, like conductors, air resistance. So you can just drag and drop it here, and there we go. You have your resistance here. And if you want to move them, you just click them and then rotate them, and then press Ctrl plus R, and Ctrl R will rotate them as much as you want, and then you can delete them if you don't like that. You double click on that and you can put the values that you want. For example, for the resistance, I put the value of 200 milliohm. That is used for basically representing the equivalent resistance of parasitic resistance of the voltage source that I have. Same thing for the voltage source. The other way that you can do that is you can go to the search tab and you can just search the stuff. So for example, I'm deleting it, but the value of the inductors that I have is here 10 picohenry. You can put whatever value that is required for the case that you are doing this. For the sources, you have E. For the voltage sources, you can just drag and drop it here. This voltage source, you can change the name or also the characteristics of them. Right now I have the E1 voltage source, and it's a time controlled trapezoidal. The amplitude of voltage is 13.5 volt, and as you can see, I set the rise time and fall time to be 1 microsecond, and the pulse width is 1 second. And these are basically the normal things that you can do in this place. You have FMTRB. So one thing you can do is you can basically search the name, or you can search basically the. So this is a force meter. So one thing you can do is, instead of searching force meter, you can either search force meter and press enter, and then you get like the elements here. You don't care about the VHDL AMS one. You go with the non-AMS VHDL AMS model, and unless if you want the VHDL AMS and you're already working with that, then you go with the VHDL AMS model. But other than that, you just go with the normal one that they provide in the Simplorer. And you have two different ones. You have the TR and TRB. So you go with the TRB one. Since you are not actually caring about the velocity force representation, you're actually looking at the displacement force for the actual armature. So you can basically here take it and then bring it over here, and then you can move it, and then you have your force. Or you can, in the other way, you can actually say FM underline TRB and then search for that keyboard, and you can see that you have less results and it's faster to get to the point. So here we are looking for the displacement force, and we have two, one VHDL, one non-VHDL. So we go with the non-VHDL version and just bring it over. Same thing. It's very fast to do that. So you do the same thing for the other parts as well. As you can see, sorry, I'm gonna put this back to get more real estate for the circuit, so you can see the circuit in a better way. Now Control D to focus. We have this limiter, and if you go inside, you can see that the limiter is acting like in a spring, and we want to make sure that we have this upper limit position of 0.006 inch, which is basically what we go up at maximum for the armature, if you remember in the model. And we put this value as like a spring rate of 10,000 Newton per meter, and the damping of like a 10 million, and the damping of like a 1 million Newton per meter. Whatever coefficients that you want to put, actually you can put it here. The mass is basically representing the mass of the armature, and here we have like 19 gram armature, and the initial position is at 0.006 inch. If you remember, that was the initial position of the armature. So we say that and press OK on that, and for the meter you don't need to do anything. The force meter will do it, would do the job. And also we want to have a force source that basically creates some source of force for you. I'm not actually very familiar with the mechanical side, so if I go banana sometimes, please apologize, accept my apologies. But anyway, so this force is basically here to act like a load or like an excitation for the mechanical side. So I added like 150 Newton of force here, and that's it. So you can just press OK, and you have your model, you have all your stuff. And by the way, you may ask, how did you find the ground for the mechanical side? And I had a hard time to find it. If you search in the library, you get different grounds, so you don't want to actually bring a component here. You basically use the same ground that you have for the electrical side, and as soon as you drag it here, sorry, you have to click on it, or Control G, and as soon as you click it here, it becomes the mechanical ground. So it's redundant here, but anyway, so it will change the look here. Okay, that was the software, and now the only thing that is remain is to go to the project and check out our TR, the transition analysis, and over there you just want to go and edit. I want to end at 5 milliseconds. You can make it 10 milliseconds, and the minimum time step is 1 microsecond. The H max, I'm gonna make it 2 microseconds, and that's it. I don't want to put any initial values or anything else. I just press OK on that and right click on TR and analyze. So now you should be able to see the analysis results. Oh, by the way, I forgot to say, the same way that you do adding the results, you can right click on the results here and create a standard report and rectangular plot. And over here we can have force, for example. The one that we are looking at is not here. Actually, you have to go to the all, and then here you basically look for the force. Actually, I think, oh yeah, one thing that I forgot to say, which was very important, is you double click on the equivalent circuit and you go to the Quantities tab, and over here you say, you know what, I want the data Simplorer database, SDB. You want to get these things out of the Simplorer database, and I want to be able to present it in the results. So you first click on FZ out, which you are interested to see, and also for the SDB you go and select current on I current 1 SDB. Okay, you can also select on N current 1, which is for the 20 for the number of turns, and it's not amp per turn, but if you want you can select that, but like this 2 is enough for us at the moment. So you just press OK on that. Now when you solve the TR, you basically get those things out from the Simplorer database. So now if you go to the result and you go to the create standard report, and you go to the rectangular report, and if you go to all, or you can go to force if you want just to get the force out, I should go to all actually. Now you can see that ECE1, that's the equivalent circuit extraction that I have here, number 1, and you can see here that FZ out, I can see it, and I can put it in a new report. I have it right there, so there we go. And if I want, for example, the mass, I can check out the mass. So that's the mass, as you can see, the result. right? And if you want to basically check the I don't know, like the current, you go to the current and you say I want that as well, so you can see the current as well. So this is the current going from 0 all the way to 62 something, whatever, and it basically settles in that. So basically when you have this trapezoidal voltage, it will causes this current and it will saturate on that, and you have this much of force. This is your force, and as you can see, everything is now plotted out, so you can actually follow that and use that later on for your result. Okay, I hope that this was useful for you. I went through a lot of trouble to gather all the information together and fix things up. I hope that you liked what you see. If you have any questions, please ask and put a comment down below. Also, you can subscribe to this channel and you will get the most updated tutorials as soon as they released. I'm trying to have one tutorial per week, which is 3 to 4 videos, or 2 tutorials per week if I have enough time. But you know, always let me know how was the performance, and let me know if you liked it.